For years, Pluto was often imagined as a distant, frozen world sitting quietly at the edge of our solar system. After its reclassification as a dwarf planet, many people assumed its most important discoveries were already behind us. But Pluto has repeatedly challenged that assumption. When the New Horizons spacecraft reached Pluto in 2015, it revealed a landscape far more complicated than scientists had expected. Instead of a simple ball of frozen material, Pluto displayed enormous mountains, broad plains, glaciers, fractures, and a remarkable heart-shaped region that quickly became one of the most recognizable landscapes in planetary science. And the mystery did not end there. Pluto possesses a thin atmosphere dominated by nitrogen, along with smaller quantities of methane and carbon monoxide. Because Pluto follows a highly elliptical orbit, its distance from the Sun changes substantially over time. As sunlight warms parts of the surface, frozen nitrogen and other materials can transition directly into gas, temporarily strengthening the atmosphere. As Pluto moves farther away, some of those gases can freeze back onto the surface. This creates a fascinating seasonal cycle. But the real question is how long Pluto's atmosphere can remain active and how energy moves through this extremely cold environment. Scientists are also interested in Pluto's hazes. Layers of particles high above the surface can interact with sunlight and produce complex chemical reactions. These processes may create organic molecules known as tholins, which can give parts of Pluto and its moons their distinctive reddish appearance. None of this means Pluto contains life. Organic chemistry is not the same thing as biology. But it does show that even a tiny world at the edge of the solar system can host surprisingly complicated chemistry. Then there is Pluto's surface. One of its most extraordinary features is Sputnik Planitia, a huge basin filled largely with nitrogen ice. Its relatively smooth appearance suggests that the surface has been renewed over geological timescales. Scientists have proposed several explanations for how such a feature developed and evolved. One possibility involves slow movement of volatile ices across the surface. Another concerns the internal structure of Pluto itself. Some models suggest that Pluto could contain a subsurface ocean beneath its frozen outer shell. If such an ocean exists, it would not be a warm tropical sea like those on Earth. Instead, it would be buried beneath enormous amounts of ice and influenced by pressure, chemistry, and internal heat. That possibility changes the way we think about Pluto. A small world this far from the Sun might still possess a surprisingly complicated interior. Where would the energy come from? One possibility is radioactive decay within Pluto's rocky interior. Over extremely long periods, radioactive elements can release heat. That heat could potentially influence the evolution of an icy body. Pluto's moons add another layer to the mystery. Its largest moon, Charon, is enormous compared with Pluto itself. The two bodies orbit a common center of mass located outside Pluto, making the system look more like a binary pair than a traditional planet and moon arrangement. Charon also has a fascinating surface, including enormous canyons and a reddish polar region. Scientists believe some of the reddish material may have formed from methane escaping Pluto's atmosphere and eventually becoming trapped near Charon's surface, where radiation transforms it chemically. In other words, Pluto and Charon are not isolated worlds. They can interact through material moving between them. And this raises a much bigger question. How many apparently frozen worlds throughout the outer solar system are actually dynamic beneath their surfaces? Pluto may not be a miniature Earth. It may never have liquid water exposed on its surface. But it has shown us something equally important. A world does not need to be large, warm, or close to the Sun to be scientifically extraordinary. And the deeper we investigate Pluto, the more complicated its story becomes. Perhaps the strangest thing about Pluto is not its distance from the Sun. It is how much activity may be taking place on a world that appears, from a distance, completely frozen. Pluto's surface contains enormous variations in terrain. Some regions are covered by bright nitrogen ice, while others are darker and richer in complex carbon-based compounds. Its mountains can rise several kilometers above the surrounding landscape, and many are composed largely of water ice. At Pluto's temperatures, water ice behaves more like rock than ordinary ice. That means these mountains can remain rigid even under conditions where nitrogen and methane behave very differently. Then there is the possibility of cryovolcanism. On Earth, volcanoes release molten rock. On icy worlds, the process could involve slurries or fluids containing water, ammonia, and other volatile materials. These hypothetical cryovolcanic processes could reshape a surface without requiring the extreme temperatures associated with conventional volcanism. Features such as Wright Mons and Picard Mons have attracted attention because of their unusual shapes and relatively smooth surfaces. Scientists continue to investigate whether these structures could have formed through cryovolcanic processes. If Pluto has experienced such activity relatively recently, it would provide important evidence that small icy worlds can remain internally active long after their formation. But there is still another mystery. Why would Pluto retain enough internal energy to support geological change? Radioactive decay is one possible answer. A subsurface ocean is another. Interactions between Pluto and Charon may also have influenced the system's early evolution, although the exact history remains uncertain. Pluto's unusual orbit adds another layer of complexity. It travels around the Sun on a highly inclined and elliptical path, and its orbital relationship with Neptune is remarkably stable. Pluto completes 2 orbits around the Sun for every 3 completed by Neptune, creating a gravitational resonance that prevents the two worlds from making close encounters. Some theories have also proposed the existence of a distant, undiscovered planet 9 that could influence the orbits of objects in the outer solar system. However, Planet 9 has not been directly detected, so its connection to Pluto remains hypothetical. This is an important distinction. Pluto is already strange enough without needing an undiscovered planet to explain every mystery. And while some speculative ideas have suggested that Pluto could have originated elsewhere, there is currently no established evidence that Pluto is an interstellar object captured by the Sun. Its known characteristics can be studied within the history of our own solar system. What we do know is that Pluto continues to surprise scientists. Its atmosphere changes with the seasons. Its surface contains enormous regions of volatile ice. Its terrain shows evidence of geological processes. Its moon Charon has a complex landscape of its own. And its interior may be far more complicated than anyone once imagined. The James Webb Space Telescope can contribute to this story by observing Pluto in infrared wavelengths and studying aspects of its atmosphere and surface chemistry. But Webb does not provide direct proof of underground oceans, active volcanoes, or life. Those possibilities require evidence from multiple observations and, ideally, future spacecraft missions. That is what makes Pluto so interesting. We are still working with a limited amount of information. New Horizons gave humanity its first close-up view, but the spacecraft performed a rapid flyby. It could not remain in orbit around Pluto for years. A future mission that entered orbit could potentially answer questions that remain impossible to resolve from a single encounter. Does Pluto really contain a subsurface ocean? How active is its interior? How does its atmosphere evolve through its long seasons? And what processes created its strange and beautiful surface? For a world once dismissed as a frozen leftover at the edge of the solar system, those are remarkable questions. Pluto's demotion did not make it less interesting. In some ways, it made its story even more fascinating. Because planetary science is not simply about counting worlds. It is about understanding them. And Pluto has reminded us of something humanity repeatedly learns whenever we explore the unknown. The universe often becomes most surprising when we finally look closely at something we thought we already understood.